Great. You don't need to put the there.
Yeah. Thanks for this nice introduction, Pascal, and for giving me the opportunity to present our recent work on optimized circuit cutting for QAOA sampling tasks. And this was joint work with some of our colleagues. Before going into details, I want to give a quick introduction, rather high-level introduction to circuit cutting, because I think it's not super familiar with some of you, because it's rather, like, say, a special technique. And just as a disclaimer, I'm not an expert either on circuit cutting, it's my colleagues, but I try to give a high-level introduction. So circuit cutting is a technique that allows you to decompose a large quantum circuit into smaller fragments. And there are two types of circuit cutting. The one is wire cutting, where you actually cut a qubit wire. And there's another technique that's called gate cutting, where you actually cut a 2-qubit or multi-qubit gate into single qubit gates. And so the point is, the method we're focusing here is wire cutting. And you replace a qubit wire by some typically measurement channels in a specifically basis and a state preparation channel, this phi I. And what will be important later is that for some techniques, the state preparation depends on the outcome of the measurement psi. And in that case, we need classical communication between the two participants. But there are also techniques that do not have this property, right? That there doesn't need to be a flow of classical communication between the blue and the orange fragment. That means that the measurement outcome here, psi I, does not influence the state preparation phi. And what you can do with this is you can reconstruct the expectation value of an observable that you would have gotten from the uncut circuit, right? So particularly what you cannot do is you cannot recover the entire bit string distribution, right? So on the left-hand side, if you have some quantum circuit and you sample from that, you will get the distribution of bit strings in the end. That you cannot recover by circuit cutting, but what you can recover is an expectation value with respect to that bit string distribution by running multiple smaller circuits. Great. And the price you have to pay for having smaller quantum circuits is that it incurs a sampling overhead. That is simply the number of additional samples that are required to estimate the expectation value to a given accuracy. And in fact, that sampling overhead is kappa to the power of 2k, where kappa is some constant that is, in our case, 3 or 4, that depends on the cutting technique, and this k is simply the number of cuts. So the important point here that it's exponential in the number of cuts, the overhead, the price you have to pay. Okay, what we're doing here with circuit cutting is we combine circuit cutting with classical size reduction techniques for QBU in order to reduce this k, right? That incurs this large sampling overhead here. And what we also do is we investigate, so what happens if you really apply circuit cutting to a pure sampling task? As I already said, circuit cutting is not intended actually to recover bit string distributions, but it's originally intended to recover expectation values. And we were able to show that you can actually do this, right? You can apply circuit cutting to a pure sampling task, and for this, of course, we took QAOA sampling solutions from a QAOA. So from a QAOA perspective, you could do like easily the existing techniques for the optimization, parameter optimization, because there you want to evaluate the expectation value, and you can do this with circuit cutting if you like. But in the end, you want to retrieve bit strings, right? Solutions. In the end, you need to sample, and this is typically where circuit cutting is not intended for. And we were able to show that you can do this, and you actually also incur a sampling overhead. And in fact, that scales even slightly better than if you want to do the original purpose of estimating expectation values. But still, it's exponential in the number of cuts. That's the point here. And yeah, and we combine two cutting techniques such that we have only one-way classical communication. I already mentioned that. That allows us to do the whole sampling on one device where we run the circuit partitions sequentially. Like we do not need two quantum computers that work in parallel and have a real-time communication link, but we can really do one device and sequential execution of circuit batches. Okay, that's nice. So yeah, and we do a proof of concept implementation of this whole workflow. I'm going to present you in a minute on quantum hardware. So this is the overall workflow. We have our problem. I took the TSP here as an example problem, that's really not important. You can do any one you like. You have to model this as a cuba. We heard a lot about this today already. And what we then do is we transform this into a max cut problem. This is actually straightforward transformation. And the point is, for the max cut, we have developed a size reduction technique that allows us to reduce the size of a max cut problem and in a, say, controllable way. And we do it that in such a way that actually you see here that the red point here is a what is called a vertex separator. If you remove that one, then the problem totally decomposes. And we do the technique, which is called graph shrinking here, in such a way that in the end you have a graph that has a vertex separator of low cardinality. Okay? So the red cloud here is actually a vertex separator, but it has not a low cardinality. Okay? And what we do with graph shrinking is we construct a graph that has a low cardinality vertex separator. And the idea is, or the point of this graph shrinking is that you can actually recover a problem from the smaller instance to original problem. Okay, then what you do is you construct the QAO circuit from that instance, and that gives you blocks of RCC gates. So the blues here, the blue, so this is P equals 2, okay, it's a two-layer QAO, and you can arrange the RCC gates, of course, in such a RCC layer as you like, because they commute, and you can rearrange them such that all of the blues corresponding to the blue partition here are on the one side, and one of the greens are on the other side. And then you see that there's only one qubit corresponding to this single vertex separator here that actually interconnects those. And those we're going to cut, okay? And we do in such a way that we only need classical communication from the upper to the lower partition, okay? That means that here, this state preparation here actually depends on the measurement outcome, but here this is not the case. And this allows us to really do this sequentially, to first run the blue partition and just keep track of what measurements we got, and then after this, just run the whole entire shots for the green partition. But I will come to this in a moment. Let me go to this whole process step by step. I guess this modeling step has been talked about a lot today already. I'll just quickly go over this. You know what a cube is, what form it has, and for the standard quadratic TSP encoding, I guess you have seen that already today, so I can be very briefly this. So in principle, you have binary variables encoding which vertex you visit at which time step. Okay. Now the more interesting thing is the transformation of qubit to max cut. Actually, this is known for, I don't know, say 60 years or so, but it's not super present in literature. That is, you can any qubit transform into a weighted max cut instance that has n plus 1 vertices in its graph. Okay, so you have, for each qubit variable, you have you have a corresponding vertex. So you have n vertices, but when you have n qubit variables, and you have one additional vertex that's called 0 here, right? And the weights are chosen in such a way that between vertex I and j, you have the corresponding qubit values. And for this additional vertex, you have this, you have, so to say, when you have the qubit matrix, you sum over the specific row and column corresponding to I, and that is what is giving you the weight of 0i. And the point is, if you do this and calculate, if you take this transformation, qubit variable xi1 takes 1 exactly if and only if the corresponding edge is 0 in the weighted max cuts instance. And if you do the math, it turns out that this is a linear transformation, okay? So if you have a qubit solution that has a value of q, then the corresponding max cut will have minus m over 2 plus some constants, where this m is the cut size, okay? The whole point here is that there's a linear transformation from qubit to vector if you pay the price of adding one additional node in the max cut graph. Okay, that's the whole point here. And what is actually, why do we transform this into this max cut? Because for this max cut, we have developed a technique that's called graph shrinking, which allows us to reduce the size, okay? And before doing the graph shrinking, we first calculate a vertex separator. We do this via integer programming. This is an integer programming model that actually calculates a beta balanced vertex separator in the original graph. And this vertex separator means that you have a subset of vertices. If you replace them, take them out of the graph, then the graph decomposes into at least two partitions. And in this example, this is the red cloud here, okay? We pre-compute this. And then we apply this graph shrinking technique that allows us to reduce the number, to replace a given subset of vertices, in this case the red cloud, by a given smaller number, in this case just one, okay? And what we do here behind is that we solve a linear relaxation of max cut and take the to do some like intelligent rounding procedure, and that's more or less it. Okay, I don't want to go too much into details of how this works. The point here is that we use linear. Great, and then we have this we construct the QoR circuit from this. We have seen this already today. That's rather straightforward. Again, you can do this in such a way that you have this single qubit line here that corresponds to this vertex, which separates the entire thing. Then we apply circuit cutting, and we use two different techniques. As I already mentioned, the first one requires actually classical communication, but you have a lower constant kappa in the sampling overhead of 3. And the second one does not require classical communication. This is therefore has a larger core. And this actually ensures that you have only one-way classical communication, right? From the top to the bottom, not the other way around. And this allows us really a sequential execution. We can actually run the entire circuits for the blue partition first, save the measured outputs, and then run the greens afterwards on the same device. Yeah, that also allows us to really do this in batches. So like we have to do one blue and one green, one blue, do 2 batches, 1 blue and 1 green. Okay, that is nice from a practical perspective, because then you don't need 2 quantum computers that have real-time communication. Just give me a quick overview of our results. This is for a 25 vertex max cut instance, which has this vertex separator of 3. And what we see here is that the distribution of the objective value, so 1 means optimal here, on a simulator if you do the cut and the uncut circuit, okay? So green is the uncut and blue is the cut circuit. On an ideal simulation. That's what I really said at the very beginning, is that you cannot recover bit stream distributions. So what we see here is that the probability distribution of the cut circuit is shifted to worse values, right? So because lower is worse here. And that's actually expected. If you do the math, you see that you cannot really guarantee that you recover the original distribution. But what you can do is you can only give a lower bound. So in principle, we know if that there's a green bar of a given height, we know that the blue bar will be larger than this height of the green divided by some constant. That's basically what it can prove. So this is expected, this is okay. So cutting actually ensures this worsening of the distribution. But the point is, if you run this in hardware, actually it changes, okay? So now the blue distribution, which is the cut circuit, is even better than the uncut one. And this is due to noise reduction for smaller circuits. So here, the original circuit has I think 21 qubits, something like this, right? So the uncut circuit is 21 qubits, or no, I think even 23. And the cut circuits, they both have 12 qubits, okay? So you reduce the total number of qubits required from 23 to 12. And this, of course, comes with a large noise reduction. And this effect actually overcompensates the distribution broadening which we have incurred by circuit cutting. So the point here is that I want to make is that although in theory circuit cutting actually worsens distribution, it can in practice even improve your distribution of solutions because, well, you have this qubit reduction and also, of course, a depth reduction of the circuit. And this, of course, suppresses noise. So what we see here is instance size versus the some, well, percentile of those distributions. Here, just to have a single number, representing the quality of that distribution, we just take the 95 percentile. And what you see here is for different instance sizes, right? So green is uncut, and you see that for running on IBM, actually the quality drops if the instance size increases. Okay, that is expected simply because the noise increases. For the cut case, it's of course similar. If you run this, the blue curves on IBM, also the quality decreases, but it's not as drastically as the uncut case. And this is exactly here this crossing where we see that actually on IBM the cut case leads to a better solution than the uncut case. But of course, this for lower instances, this is not the case. So you need to have a certain instance size to actually, so that's the noise mitigation effect is large enough that it overcompensates the degrade that you incur by circuit cutting. Great, let me come to a quick conclusion. So the main point is we did this proof of principle of combination of graph shrinking and circuit cutting on real hardware. We are one of the first, I think, who applied circuit cutting to a sampling task. And what we see here is that in real hardware, if this instance size is large enough, actually the noise mitigation due to circuit cutting over compensates for the distribution broadening. And some challenges is still there's an exponential sampling over it in the number of cuts. That is, if you, and the number of cuts increases linear with the layers, right? So if you would add more layers here, then you would have more cuts, and the sampling over it would grow exponentially with the number of QoO layers. And on the other side, there are established classical optimization decomposition methods. In particular, if you start here, right, then you can just consider the vertex separator here, this red one, and assign one value to it. Say the one. Solve the two decomposed problems, whatever method, QoO, and fixing. So simply by just fixing variables, you can actually do a classical decomposition, and that has, if you think about it, a maybe even better sampling overhead. So what the point I want to make is that you have to really improve the cutting techniques here in order to overcome this exponential scaling with the number of QoO layers. And with that, I'm at the end, and I'm left with pointing you to a preprint, and I'm open for questions.
Thank you very much. So, are there any questions?
Ja, here's what the process with shrinking. If we just in the end go back to Cubo on stuff, would this be just like the Cubo reduction algorithm? Like,
yes,
so
yes.
You
can
be like equivalent, like same minimum as the first one.
Yes.
And do you think this is? I mean, do you think it's viable? Do you think in practice it does a lot, or are there some problems with it?
You mean with the like the transformation and the reduction if you apply an arbitrary keyword?
Yeah, this overhead involved.
So the theory is the overhead is fine because it's not a linear program. Fast in some sense. Okay. Practice this is going to give you a bottleneck. point is also that it's heuristic. It really depends a little on the structure if this works well or not. Heuristic means that so if everything works well, this has the same objective value as this. So you can reconstruct an optimal solution to the large graph from the small one. If it does not work well, then this is not the case. Then you cannot reconstruct an optimal solution from an optimal solution of the shrunk instance, right? So we can lose something there. That's the heuristic point. It really depends on the instance.
I have a question regarding, so you use now the circuit cutting, and there are so many other techniques of some we've seen during the course of the session, which is, I mean, qubit mapping or routing, which you also can use also an expert on that. Did you mix this with other ones? Because I mean, you see, okay, this gives an improvement, something else gives an improvement, but sometimes if you mix two that give an improvement, this won't give you any when you mix it. Or was it just solely, okay, does the circuit cutting work?
Yeah, that's a good point actually. That's a part of future work, I would say, to improve other reduction and improvement methods to this whole framework. The original point here was that we want to apply circuit cutting to QAOA sampling. And if you do it like multiple gates, multiple lines, then the sampling is huge. So in practice, you cannot really use this on hardware if you not only consider it like artificial instances that directly have this decomposition nature. So we kind of want to apply circuit cutting to a real-world QBO, and that is why we combine this with this specific decomposition technique, but you're absolutely right, others might even improve this.